So thank you very much for coming. And so I will start. So the overview of the talk is here. So I will begin with some discussions concerning the scientific revolutions and the Kuhnian theory. Then I will try to propose a classification of the scientific revolution. That means the idea is that there are different kinds of revolutions. Then I will discuss the question, how far is the theory of Thomas Kuhn and Imre Lakatos connected to this classification? It will turn out that each of them are suitable for discussing different kinds of changes. Then I will speak about the biggest changes, that means of idealization. So the change that separates Egyptian and Babylonian mathematics from the Greek mathematics. So the invention of proof, invention of rigorous mathematical thinking. Then I will speak about recodings in mathematics, so a way how mathematical language is changing, how mathematics develops different representational tools like algebra or like logic. And at the end, I will consider Fregean revolution, and we'll discuss how it is connected to this classification. So let's start with Kuhn, because actually, Kuhn's theory, Kuhn's book appeared in 1962, and in the coming period, so in the next 20 years, it was discussed also by mathematicians whether Kuhn's theory of scientific revolutions can be applied to mathematics. And in these discussions appeared as very interesting fact, or that means that if you take the Newtonian revolution, so the birth of Newtonian physics, then the previous paradigm, the Aristotelian physics, was totally kicked out of curriculum. So today nobody is studying Aristotle to learn physics. So physics department don't teach any Aristotle, they start with Newton, etc. But after the Einsteinian revolution, so when Einstein, relativity theory, etc. came, Newtonian physics is still part of the curriculum. So even today, if you study physics, you are taught Newton, you are taught how to calculate the positions of the planets, etc. So really classical mechanics. So it seems that these two revolutions differ in the way how the scientific community behaves. In the first case, the scientific community rejects the old paradigm and focuses totally on the new one. In the other case, in the Einstein revolution, the scientific community decided to include the old paradigm in the curriculum and teaching of the new science. And so it should be a fact that should be acceptable even for any Kuhnian, because in a sense, it is a way of how the scientific community behaves. So we see here that there are differences in this behavior. It's very interesting then when this was put to Kuhn, not in precisely this way, but on some conference, there were people who tried to persuade him that there are different kinds of revolutions. So Kuhn vehemently rejected it. So he said that he's not interested in classification of revolutions. For him, always there are the same problems. So the same problems of communication, of translation, etc. So basically, he was opposed to this idea, but now that he passed away, so we can maybe do it. And so the idea is to look on what kinds of changes we have in science. So it's a short idea of classification of scientific revolution. So the idea is that if you look on Newton, so the biggest change is, of course, the Newtonian revolution, where you totally change how you treat motion. So Newton invented the first differential equation, and actually you describe motion using differential equations. So Aristotle is totally useless because Aristotle is a verbal physics. It's totally different than what Newton is doing. So of course, if you have this kind of change, you really opt only for Newton. The other kind of changes are what I call recoding. So basically, when you change the total linguistic framework. So for instance, when you pass from Newton to Maxwell to electrodynamics, what is basically how people speak about Einsteinian revolution? So they speak about Einstein, but basically already Maxwell's equations are Lorentz invariant. So basically already with Maxwell starts the theory that leads to Einstein, etc. So basically Maxwell changes totally how we describe motion, because he introduces the concept of a field, etc. So, and then, of course, then Schrödinger introduces the quanta and the quantum mechanics. Again, everything is different. So basically, recordings are this passage from Newton to Maxwell or to Einstein, and then from there to the quantum mechanics. But what is interesting that in these kinds of changes, we always teach the old one. So always people teach. So today we teach quantum mechanics because quantum mechanics is the theory of the world or quantum field theory, but still we use to teach Newton and we teach Maxwell. The third kind of changes is what I call relativization. And it is very interesting if you take Newtonian mechanics, Lagrangian mechanics, and Hamiltonian mechanics. And I'm very happy that I have here a table, so I don't resist to really make at least one drawing. So what is Newtonian mechanics? Newtonian mechanics, if you look on the system of the sun and the earth. So it describes it in a three-dimensional space, that two bodies are moving in three-dimensional space. Lagrangian mechanics is another kind of mechanics, so this one, developed by Lagrange. So Newton has three-dimensional space. Lagrange has six-dimensional space. So only one body is moving in six-dimensional space. The first three dimensions relate to the sun, the other three dimensions relate to the earth. So we create a big space in order to have simple objects. So while in Newton, the two objects can have many different mutual positions, etc. So the motion becomes very complicated. In Lagrange, everything is simple because we have just simple point. The point has first three dimensions represent the sun, the last three dimensions represent the earth. So the point is moving and its motion represents the motion of the earth and the motion of the sun. So by moving one point in six-dimensional space, we are somehow representing motion of the system of earth and. But Lagrange equations are still second-order differential equations, and then comes Hamilton, who creates a 12-dimensional space. The first six dimensions are like in Lagrange, so the position of the sun and the position of the earth. Then you have the velocity of the sun or impulse of the sun and the velocity of the earth. So you have these three-dimensional vectors. So basically you have a 12-dimensional space in which the position of a point, first two dimensional says where the earth is, where the sun is, then and the last was the speed of the sun was the speed of the earth. So basically everything is represented by the space, and so the motion becomes very, very simple. The motion becomes so simple that actually in the Newtonian picture, the trajectories can intersect. You can go this way and then this way. While in the Hamiltonian picture, there is no intersection of trajectories. So the whole picture becomes much more regular, much more geometrically clear, etc. So these are really important changes. For instance, you need the Hamiltonian picture to have chaotic behavior. So to discover chaos in the Hamiltonian system, you are able to discover chaos. In the Newtonian, not. So these are changes, but they are much smaller because basically all three are about mechanics. So it's just the Newtonian theory, but represented in different backgrounds. And then the fourth kind of changes is reformulation, which was done by the young Euler. So when Euler was some 24 or 25 years long, he wrote a small booklet saying that actually Newton's Principia is incomprehensible. So if you have a problem and you slightly change the structure, the positions, etc., you cannot transfer the solution because Newton is doing everything geometrically. And you have some proportions, and if you change the proportions, things don't work. So what Euler did, he translated Newton from geometry into calculus. So basically, Newton was not using calculus in his Principia, and it's a very interesting thing that Newton discovered the calculus, but never applied it in his Principia. Principia is written in Euclidean style, using geometry, using really ancient Greek mathematics. While Euler came with the idea, okay, let's rewrite Newton into calculus. Then if I change the position, it's just a change of values of some variables. So nothing changes. So basically, these are, in my view, four very different ways what you can change on a theory. So in the first way of passing from Aristotle to Newton, you change the way how you understand motion. For Aristotle, every motion required a mover. So in order to move, you have some cause that moves you. Newton, the motion is, there are no causes. Then you have these changes from mechanics, field theory, quantum mechanics. These are radical changes, but all of them are using differential equations. So they are, in a sense, in the Newtonian mode that you have Schrödinger equation, Maxwell equations. They are variants of the Newtonian description. Or you can choose just the Newtonian stuff, but still you can do it 3-dimensional, 6-dimensional, 12-dimensional. And you can do it geometrically or via calculus. And now let us look on how this is related to Kuhn. So Kuhn's theory, in my view, can be seen as a projection of a photograph of 4 different faces on each other. So imagine that you have 4 photographs of, I don't know, your girlfriends or something, and you project them on the same place. What appears? All details get lost. What remains is the global structure of the face. So 2 dark spots somewhere representing the eyes, some nose, etc. But no details of any space on any of the faces will be preserved because, and I think this happened to Kuhn. So Kuhn is taking these 4 kinds of changes and analyzing them together without discriminating them. What happens? All the epistemological details are lost, and what remains is what is common to all of them, and that is the social structure. So the structure of how the community reacts to changes is the same for idealization, recodings, relativization, reformation. So what they have to have, there are some crises, etc. So all this Kuhnian narrative is basically sociological, not because it would be somehow important, but because he's mixing together the 4 different kinds of revolutions. So if we separate them, then we can have an epistemological understanding of each of them. And that is basically the idea of the classification which I'm working on. So really separate the 4 kinds of scientific revolutions, and each of them can be analyzed. Of course, the sociological structure is the same. You have people who believe the old paradigm, then comes somebody with the ideas that, okay, it could be differently, then he persuades some people, then the most will be persuaded, and etc., and then they win. So the revolution, the social dynamics in all the cases is basically the same. And that's why Kuhn's theory is sociological. And it holds also for Lakatos. So they are describing patterns which are very robust, but so insensitive to details. And I try to make the classification. And if you try to classify them, then you see that Kuhn's theory, I put here 2 points, that for idealization, it's very good. It works very well because you have a basic paradigm. So you have a paradigm of Aristotelian physics, Earth is unmoving, etc., and everything is working. And then something changes, and you have Newtonian physics. And what changed is really the persuasion of the people, the whole social milieu. If you have recodings, so the Kuhn theory is, because what is important for Kuhn is the incommensurability. So you cannot communicate between the paradigms, etc. So they are living in different worlds. So I suppose that Kuhn is so well known that it's not important to really present his theory again or repeat it, but basically his theory is very good, well applicable if you take the transition from Aristotelian to the Newtonian worldview. So there is no point today teach Aristotle because they are not communicating. So that is why here I put 2 points, that in the case of idealization, the Kuhnian theory is fine. In kind of recodings, it still captures something, because if you have a relativistic description, it gives you different results than the non-relativistic ones. So basically, they are different. The theories differ, the predictions differ. The perihelium of the Mercury or anything is in one theory gives different answers than the other. So they are not translatable. You cannot have a huge theory that covers both of them because they are different. Then you have relativizations where I think that, Hamilton and Lagrange, they knew that they are doing the same job as Newton. The theories are slightly better, so you can solve some problems in the Lagrangian manner, which you cannot solve in the Newtonian, etc. So the theories are slightly better, but very nicely translatable. So everything that one says about the sun is true in the other ones. So Hamilton is able to say something more, but everything what Newton says, Hamilton says it's true. So there is a good translation, it's a conservative. And of course, reformulations, there is no point in bringing the Kuhnian all heavy, vocabulary if you take Newton and Euler. So Euler was trying to rewrite precisely what Newton was saying. So there is no shift of meaning. He's trying to do the same thing, just using different mathematics. If you look on Lakatos, the situation is opposite. So if you would say that, okay, I would have the idealizations as a scientific research program, it even doesn't make sense because, they are so far away from each other. So Aristotelian science and Newtonian science would be the same research program. There is nobody who would really try to develop it, etc. So their Lakatosian point of view doesn't make much sense. In recoding, so in, say, seeing entire physics, because what is typical for Lakatos that he is operating on two levels. He has something like the core of the program, and that's why idealization cannot be a Lakatosian program, because the program has to have its metaphysical core and then the protective belt. So you have somehow parts of the theory that you can change and part of the theory that you cannot change. And I think that these two parts are sitting on different layers. And of course, from idealization, you don't have any higher layers, so there is nothing that could work as a hardcore of the program. So if you take recordings, okay, so the idealization would present the hardcore and the recordings would present the protective belt. Then you could see entire physics as one scientific research program. I don't know whether this gives you much, to really try to cover Newton and Schrödinger and everything into one research program, but okay, maybe it could. But where it does make sense is really to see the relativization. So what the one kind of coding is the core of the program, and then these heuristics are basically the relativization. So the transition from Newton to Lagrange to Hamilton can be seen as a program, and basically Lagrange was understanding what he's doing is as a development of the Newtonian mechanics. So in Newtonian mechanics, you have the three-body problem, and it's very difficult, and Lagrange tried to solve it, etc. And of course, the reformulation is, that means that the core of the program is here, and the protective belt is here down. It's a very natural, and it's the best way how the Lakatosian program can be understood. That means that Lakatos works on two layers. On the higher layer, you fix what is unchanging. So basically, you choose, for instance, Hamiltonian mechanics, and then you develop it, programs, problems, etc., and go on. So I would try to suggest that basically Kuhn and Lakatos are speaking about scientific change on different scales. Kuhn is speaking about changes on large scale, where the communication is lost, where basically you have paradigms which are not translatable, etc., maybe incommensurable, etc. So he is very well applicable to idealizations, slightly, but still very well applicable to recordings, and he doesn't make any sense to see reformulation as a revolution. On the other hand, if you take Lakatos, so the examples he gives, for instance, he describes the Newtonian research program, how Newton developed his model of the solar system. So he said that first he worked with points, so planets were points, then planets were small balls, etc. So really getting more and more details into this program, he developed the program, but what was going on, it was still the development of the same relativization, so it was still in the three-dimensional Newtonian framework and was working here. So Lakatos is better working for the small changes and doesn't have much sense for the big ones. So that's why if you would like to capture some kind of phenomenon in the history, the question is on what scale are you working? And if you are working on a big scale, choose Kuhn. If you are working on a smaller scale, it's better to choose Lakatosian. So I think this is very interesting because it shows that the classification makes it possible to really be more precise in both cases. Now, there's my book, which was both here. So it's interesting because the book doesn't have a first chapter. So but nobody recognized it, and it's a secret. But because it had the first chapter about idealizations, about the biggest changes, but I was not able to write it on mathematics because in mathematics the idealization happened between Thales and Euclid. So between 6th and 3rd century BC, somehow the Greeks invented proofs, invented definitions, invented axiomatic systems. So this somehow developed, but we don't have any data. We don't have any manuscripts before Euclid. So from the time before Euclid, there are very few short fragments, and that's it. So no really mathematical works are preserved because, in order to preserve a work from ancient Greeks, you have to rewrite it word by word every, say, 50 or 100 years, because the papyrus is deteriorating and you have to make it, like the Jews in the synagogues, they are rewriting the Bible every, I don't know how many years, because it's destroying. And so, and why would you rewrite anything that is older than Euclid? So Euclid is so good that there is no point in bothering about the mathematicians before him. So we have no data about how this process of idealization happened in Greece, but we have a good data about how it happened in physics. So the first chapter of the book was about Galileo, Descartes, and Newton, and how the idealization in physics went. But the editor of the book told me that actually I shouldn't put it there because the physicist will tell that there is too much mathematics, I'm not interested. Mathematician would say, oh, there is physics, I don't understand it, and nobody would read it. So I kicked off the first chapter. There's no first chapter, no idealization is in the book, and so the book is just, of course, I numbered it so it doesn't appear that it's not there, but there is no theory of idealization. But in between, I was able to, so the book appeared 2008, so it's about 16 years. So in between, I developed a better understanding of idealization. So how really idealization works and what is idealization about. And so this is the idealization of physics, but basically, okay, I will describe it and then show how it works in mathematics and before. So the first very important thing is phenomenal reduction. So what physics do is to measurement. And basically it reduces every phenomenon to a number. For instance, color, Newton was able to reduce colors to the angles of fraction. So different colors have different angle of fraction. And so he measured the angle and got the reduction. So if he would have an assistant who was colorblind and ask him that what color is this sweater, he would put it before the prism, and then the light would go, and he would measure the angle and would say red, without having any idea what is red. So you don't need to know what is red. You can be colorblind. You can still do physics because it's about the numbers. So that's the first. Now, why do we do phenomenal reduction? It is because of the relational synthesis. So I measure color, so for instance, there is this famous law of Galileo that the spatium, in free fall, the distance is proportional to the square of time. But what is square of time? Have anybody of you experienced square of time? How many square seconds has a square minute? And how is it flowing? So, if you have a square minute, so in the first it's 1, then 3, 5. So how is it really going the square of time? Nobody knows. In space, we have access to the length, area, volume. Fourth dimension, we don't have. But okay, so we have very reduced or very little access to the phenomena. But if I measure time, mathematics give me all the powers and logarithm of time and exponential and sinus, etc. And I can build many formulas. So that's it. So we reduce in physics, they reduce the phenomena to numbers because this opened up a really incredible amount of mutual relations between the phenomena, which in the real world you cannot see, you cannot observe. I cannot observe this. And what was actually Galileo measuring was time. He measured time and measured distance, and then he found out that the relation is this one. And of course, if you take Planck's law, there it's depending on the wavelength of the light or on the color. So we have a formula which gives you the intensity of the radiation of the black body, and it depends on the color. So, you have a formula that gives you dependence of the energy on the color. So really, the phenomenal reduction is important, but still, it's not everything. So then we have ontological reduction, just the second step, and that is the introduction of a concept of state. So in mechanics, electrodynamics, quantum mechanics, always you represent something which physicists call the state of the system. And why is it? Because you need compositional synthesis. And what is compositional synthesis? It's a very interesting thing because, of course, science is interested in complex structures. And you have to build somehow the complexity from the simple. But, and it is very interesting, if you look on Copernicus or Ptolemy or Tycho Brahe, they are all doing geometry. That means they are having geometrically ordered trajectories of the planets. And what is Newton doing? Newton is having bodies that interact. That means that the compositional synthesis of Copernicus is geometrical. The order, how the planets are put together, is a geometrical order of the orbits, etc. While in Newton, the compositional synthesis is physical. So what keeps the planet on its orbit is the force, and the bodies are interacting. I'm saying that, I'm calling it that the physics of Aristotle or the Ptolemaic system or the Copernican system, it's autistic physics. That means everybody is doing what he's used to do and ignores the rest. So a planet is moving on a circle, but independently of what the other planets are doing. In the Copernican system, it just goes round, etc. Doesn't care for the others. While in the Newtonian system, the system moves as a whole. So everybody is somehow attracted by the other bodies, and the dynamics is a general dynamics of the whole system. So that I try to express that we have physical compositional synthesis, where we compose dynamics and we get complex dynamical systems. And we have geometrical compositional synthesis, where we simply put together the trajectories and get a nice geometrical picture without any dynamics. And in order to be able to make a physical compositional synthesis, you need a notion of state. So what is Newton doing? He is having several bodies in space, which are in dynamical states, and together they interact and form a dynamical system. So basically, very important thing is how you introduce compositional synthesis into your theory. And this is even not the last point, because the last point is the causal reduction. The causal reduction was done by Newton when he said that every interaction is action of forces. So whatever happens in the world, it happens because some forces act on bodies. And this is, so we have these three reductions. So we reduce phenomena to numbers, we reduce ontology to the states, and we reduce interaction to action of forces. And why do we do it? Because I can insert the forces into the differential equation. So the second law of Newton, F is equal to m times a, was the first differential equation in the history of science. And it is the new way how you describe motion. How you describe motion, you look how the state is changing under the action of forces, and you describe it by means of differential equations. So basically, what is idealization? Idealization consists on three reductions. I reduce the phenomena, I reduce the ontology, I reduce the causality, and put them all together, I get a differential equation that allows me to calculate the future. Of course, nobody believes today to Laplace that he said, that if I would be clever enough, I could calculate all the future, all the past, etc. So if Laplace would be interested in the independence of or incompleteness of arithmetic, he would just calculate the state of the world until 1931 and look on the Mathematische Annalen, and there he would find the answer. So basically, really this deductive synthesis, the way how you can calculate the future of the dynamical system, that's the big invention of Newton. Until Newton, nobody was able to predict the future. And I call this idealization. So idealization is three kinds of reduction by simplifying the phenomenon. So you have color, but you are not interested in color. You have just one number that gives you the wavelength. You have heat. You are not interested in how you feel heat or, etc. You have just one number. So if you reduce the world to numbers, if you reduce ontology to just the state of the objects, etc., then you get this description. Now let's turn to mathematics. And mathematics, of course, what is lacking here is the causal reduction. Why? Because we don't say that the circle is somehow acting with a straight line. The straight line can intersect the circle, but the intersection of the line and the circle is not an interaction. And that is very interesting because if you read Euclid is a fascinating book, and there everything is in past tense. So everything is already done. So there is no active verb. All verbs in Euclid are passive. So the straight line already is intersected by the circle. The point is already there. So Euclid is not doing anything because he read Plato, and Plato wrote that actually mathematicians are crazy. They believe that they can add two numbers. But numbers are abstract objects. How can you add two numbers? Can you, 1 plus 3, I take 1 and plus 3 and put them together and then I get 4? I cannot do it because it's already done. So for Euclid, everything is already happened. So nothing is interacting with nothing. It's totally a temporal, eternal world of mathematical truth. So we don't have interaction. So that's why we don't need this. But basically what we have is the phenomenal reduction. It's of course, I have here this table, but I see here, what is it? Not a square, but a rectangle. Of course, this is not a rectangle, etc. So, from a mathematical point of view, this is not straight enough, this is not right angle, etc. But okay. So the phenomenal reduction is a reduction of what we see or what we have by ideal mathematical objects. It brings up the relational synthesis. It's of course the proportions, etc. So all the precise mathematical relations that exist between the abstract geometrical objects. Then the ontological reduction is something what was invented by Plato. So the Plato's realm of mathematical objects, he realized that actually mathematics requires ontology. Okay, then comes compositional synthesis, and this is the big discovery of Euclid. It's very interesting that many historians consider Euclid as a compiler, that he took results of many mathematicians, put them together, and edited the work. But I think that Euclid is much more important, much more creative man, and he invented the compositional synthesis. What does it mean? This is the construction. Of course, he doesn't construct anything because all the constructions are already done. But the idea that you have primitive objects, that you have circle, straight line, and points, and if I have here a rectangle, I'm not speaking about rectangle, I have to construct it. So everything in Euclid is, so if you look on Euclidean proof, in every Euclidean proof you have a construction and then a proof. So we are proving about the constructed object. So I see a pentagram, but I say, oh, I have to construct the pentagram. And only based on the construction, I base my steps of the proof, and the steps of the proof follow the steps of the construction. Because if I do I think Kant was totally right that mathematics is necessary because we did it. So, I take a pentagram, but I reconstruct a pentagram by means of ruler and compass. And all the properties it has come from the construction. And so I know everything what is true about a pentagram because I constructed it. So geometry is not about objects that we can find around floating somewhere. Geometry is about objects which we construct. And because we construct them, we can prove about them all the terms which we need. We will see it working on logic. But before mathematics, of course, there was something much more simple. And this is arithmetic. This is mathematics of Babylonia, Egypt, India, China, etc., which was based on counting. Now, counting, the most important point in counting is the unit. And Euclid has a beautiful definition of unit. Unit is that after which everything is called one. So if unit is man, then 1, 2, 3, 4, 5, 6, 7, 8 people. If unit is a leg, then 2, etc. If unit is a finger, and unit is a teeth, then it's much, much more complicated. So basically, by unit, you are very different from your colleagues. So, but if I'm counting man, you are just as he, a unit among us. So basically, the unit is the phenomenal reduction, and it opens up a relational synthesis because we can compare numbers. If I have a heap of, what is Streichhölzer? Matches, a heap of matches and another heap of matches, and I ask you which is bigger. I don't know whether you have seen this American film with Hopkins, with Rain Man. So, so somebody threw the matches on the floor and he said 48. So he looked and saw it. But we are not able to do it, but we have numbers. So I count one heap, count other heap, and say here there are more. So the relational synthesis is something which allows me to relate the two heaps, which on the phenomenal level, I cannot grasp. I don't know that, I don't see that whether there is 48 or 50 or 80, but if I count it, etc. So, but then there is no ontological reduction. So arithmetic is not about ontology. It's about phenomena. It's about how much I see, what is there, etc. So basically, the compositional synthesis is precisely related to relational. So if I ask how much is 7 plus 5, I take 1 from 5 and put it to the 7, etc. So basically, with manipulating with the units, so with what I get in the phenomenal reduction, I can make all my counting. The parallel axioms are saying precisely that I don't need any ontology. It just, if I have a units, I can manipulate the units and I have everything I need. And the deductive synthesis are the rules of calculation. So basically what we teach children in school. So my view is that we have 3 ways of idealization. The one is what was done in 17th century by Newton, and it has this phenomenal ontological and causal reduction. The other was done 300 BC by Euclid, and it lacks the causal reduction. And then we have the one that was done 2000 years BC in Egypt, Babylonia, etc. And it doesn't have any ontology, it doesn't have any causality, it's just on the phenomenal level. And so this is about idealization. Recodings is, of course, something that I have in the book, in the patterns of change. So this is basically, if we say, okay, let's take mathematics. So how mathematics developed. And this table is taken, not the table, because Frege is not interested in geometry. So Frege has only this algebra, this symbolic part, who says that actually first people were counting with numbers, concrete numbers. Then they introduced letters and had some general calculations, general formulas. Then they introduced functions and had some relations for functions. And Frege says, and if we introduce higher level functions, we make another step forward. So basically, Frege himself understood what he was doing. as creating a new mathematical calculus, a new mathematical language or representational tool, the predicate calculus, that is parallel to the Leibnizian differential integral calculus, to the Dietz algebra, or to the arithmetic. So you have some symbols and you have rules for manipulating with symbols, and that's it. And what I try to do is to put there the geometrical steps that happen in between. So algebra is, say, 800 was created by the Arabs, but between elementary arithmetic and algebra, we have synthetic geometry. And so in the book, it's described why geometry was so important, because actually geometry introduced the first general object. The first general object is a straight line of indefinite length. So if I don't say you what is the unit, then this can represent 200 or 1 meter or etc. And in this way, we have a universal language. And that is why the proofs in Euclid are general. That means if I prove something for like a Pythagorean theorem, so basically what Euclid does in his book, he is proving the theorem of Pythagoras for one particular object that is on the paper. So I can measure this length and that length and that length and say, okay, dear Euclid, you are fine, it's nice, but you proved it for this particular triangle. And what are the triangles? But the answer is, if I didn't use in my proof any properties about the length, then this diagram could represent any triangle, whatever, and so the proof is general. So the generality doesn't occur in algebra. It was not invented by the algebraists. It was invented by geometers, and the algebraists only used it or somehow introduced it into symbolism. Similarly, if you look on the functions, so of course, analytic geometry first introduced curves. But curves are, geometrical curves, geometrical representations are very limited, and Leibniz introduced the general concept of function. But again, it is very much just taking the concept of curve and developing a symbolic language that can deal with curves as functions. So this is the way how Frege understood his revolution, how Frege understood what he was doing, and how in the book I was also believing that if somebody knows what Frege did, it's him. So I believed him that he knows what his revolution was. So it was the revolution of the second kind. In this hierarchy, it was recoding. So it was kind of creating a new linguistic framework. But if you take algebra, calculus, or analytic geometry, they are all using the mathematical idealization. So they have phenomenal reduction, this relational synthesis, ontological reduction, etc. So basically the structure of all these languages is, from the point of view of idealization, the same. They are fixing this basic structure. But then I began to realize that actually, so I was believing that actually what Frege did, what are these languages doing? So what is basically new, say, in algebra? Algebra was the first language that proved negative results, that something is insolvable. For instance, algebraists were able to prove that the trisection of angle is a no-go. So there is no trisection of angle. In geometry, if you were in ancient geometry or any geometry, whatever, you can work in geometry all your life and you don't succeed. But you don't understand why. In algebra, because algebra has a greater logical power, it can prove that this is not possible. Similarly, algebra has greater expressive power. So in geometry, you have x is the length, square is the square, x the third power is the cube, and that's it. You don't have 4, 5, 6, 7, etc. because the space doesn't allow it. Algebra, of course, can express any power you wish. So that's why the basic results which were proven in algebra is, for instance, solution of cubic equations. cubic equations are geometrically very difficult to work with. Quadratic equations are equations about squares and rectangles, etc. And Euclid has proofs how to solve quadratic equations. So if you know you have the problem of having a square and a rectangle, etc., and it should be somehow something. And then he constructs the solution. But cubic equations, the Greeks were not able to solve. And of course, algebra has no problems with cubic equations. So if we sum it up, we can realize, and in the book is described, that these tools of representation have logical power, expressive power, integrative power, and explanatory power. So they are really able to prove more theorems, to describe more situations, to bring unity where there was no unity, etc. But so it's no doubt that Frege did create a new instrument of symbolic representation. So his logic is really one of the instruments. And in doing so, he increased the logical power, expressive power, etc. of mathematics. But doing so, he changed the language of logic in an even more radical way. And I will try to argue today that what he did is idealization. In order, we have to look on Aristotelian logic. Now, Aristotelian logic is a very funny thing because it lacks ontological reduction. What does it mean? It means that for Aristotle, any proposition is a relation of concepts. A is B, so for all, every A is B, or no A is B, etc. So there is basically, logic is working on the level of concepts. What Frege changed is that predication is the relation of a concept of an individual. So, you know, AX. So basically, in Aristotle, we have, so it's just a subject and a predicate. So I am reducing every proposition to a subject and a predicate. Then I can describe in what extent this A is B. So the subject belongs to the predicate, every or some, etc. And Aristotelian logic has no compositional synthesis. If you like, the only sentences Aristotle is analyzing is A is B, nothing more. So really, the propositions are simple, and the proofs, I have two propositions and then the consequence. So everything in Aristotle, he doesn't construct complicated structures. And this is the same in arithmetic. If you look in arithmetic, so in arithmetic, you don't have complicated numbers. You know, you have bigger numbers, 745, but it's just a collection of units. There is no complexity. While in geometry, you have complexity. If you take a Euclidean construction of a pentagram or something, it has many steps, etc. It's complicated. Arithmetic, the object of arithmetics are just heaps of units, so nothing more complicated. So I think that basically the structure of Aristotelian logic is a theory of an arithmetical kind. So once I told it, said it in a funny way that basically Aristotle's prior analytics should be translated into Babylonian, put on the cuneiform tables, burnt out and buried somewhere in Babylonia. It doesn't belong to the Greek culture. It is really a theory of the arithmetical kind. It doesn't have ontological reduction. And that is why it couldn't be used by Euclid. It's very strange that Aristotelian theory of syllogisms was written and known before Euclid, but nobody is using it. Even Aristotle is not using his theory of syllogisms in his biological or physical works. So he develops natural philosophy, but doesn't use logic. And my answer is that it is because the structure of his logic is very simple. It's an arithmetical theory, so a theory without ontological and without causal reduction. And now if we look from this point on Frege, so what is Frege doing? Frege also, of course, changes phenomenal reduction. So instead of subject and predicate, he has function and its argument. that enables him to change the quantification. So we have polyadic quantification, so we can quantify in minutes. Okay, I'm almost done. So then, and what is important that Aristotle has a primitive or most simple basic proposition is A is B. And Fregean said it's a composite proposition. It's composed from AX and BX. And it says that if AX, then BX. So logic is somehow ontologically grounded. So you have to relate the concept to objects, and the primitive proposition is AX. The object X has the property X, A, so it has a predicate. And then the Aristotelian A is B becomes a conditional. So if AX, then BX. And that is, I think that shows that Fregean introduced ontological reduction. That logic is not on the level of concepts. It's not a theory about relations of concepts, but it has to, we are the conceptual level and we have the object level. We have ontology and things below the ontology. And of course, quantification relates to the X. So not every A is B, but for all X, if AX, then BX. And also Fregean introduced negation, implication, and quantification as tools by means of which he created his compositional synthesis. So in Fregean's Begriffsschrift, you have formulas which are on one page, you know. So of course his way of writing is not very efficient, but okay. So he has composition synthesis. And what is very interesting that all three things were present in Aristotle. But quantification was bound to the subject. So that means that you had monadic quantification, only one quantifier in a sentence. Fregean can have 5 quantifiers in a proposition, and in calculus, the continuity of function has 3 quantifiers. For all x, there is a for all epsilon, there is a delta, so that's for x, etc. So basically in mathematics, and that was one of the motivations of Fregean, we have several quantifiers. So what Fregean did is he liberated the quantifier or detached the quantifier from the subject and attached it to the variables or arguments of the function. So, okay, so he changed monadic quantification to polyadic. Similarly, implication. Implication was present in Aristotle, but hidden in an elementary proposition. So all A R B is basically an implication. You see it on a Barbara. If you take the mode Barbara, all A is B and every B is C, that means every A is C. Is basically a connection of 2 implications. So even it is not written in this way, but somewhere there are hidden implications and Fregean make them explicit. So Fregean, in a sense, again, Aristotle had monadic implication that in any proposition, there was just one connection made between subject and the predicate. And Fregean liberated the implication from, or the conditional from the proposition. And again, you have formulas which have many conditionals. And the same thing with negation. In Aristotle, negation is connected to the copula. So A is B or A is not B. So basically, again, you can have only one negation, namely that in the copula can be positive or negative. Fregean said, no, we put the negation in front of the entire sentence. So the elementary sentence is positive, and then you can have as many negation as you wish. And I think that this is fascinating because it shows that everything from which Fregean constructs his language is present in Aristotle. But it is present in a way that is attached to a singular position. So negation is attached to the copula, quantifications to the subject, and implication to the relation between the concepts. So Fregean separates these connectives from the Aristotelian prison, so to say, and made them freely, and so he has compositional synthesis. So, and that is, I think, what justifies the claim that Fregean is really changing the structure of the language. So instead of a language of arithmetical type, which is this way, so which has this structure, so you have just phenomenal reduction, and then everything is following from this phenomenal reduction. So Frege, in a sense, introduces, so you have phenomenal reduction with its functional arguments, and then you have, the arguments are somehow ontologically connected to the objects, so you have model theory, you have somehow semantics, which is Aristotle. I don't know whether he has semantics or not, so how to construct it, but maybe this difference also explains why there is this discussion about what is it? Ontological stress or something. That means that some syllogisms don't work if the concepts are empty. And now people are trying to solve the problem by saying that, okay, all concepts have to be non-empty or something. But I think that this is wrong, because in the Aristotelian logic, there is no relation to the reality. There is no ontological commitment in this way or other, so nothing. So basically, if there are no horses, I don't speak about horses. So, so that's it. So Aristotle is not, while Frege has ontological commitment, so he has ontological reduction. And if there are no A's, then he has to deal with it because of his ontology. So he's really trying to connect the logic to some ontology. So I believe that this shows that the Fregean revolution was in relation to logic. So with relation to mathematics, of course, is true what Frege says, that we had arithmetic, algebra, then Leibniz, and after Leibniz, I'm coming and bringing in functions of second order, so truth functions, etc., and building this predicate calculus. But if you look from the point of view of logic, then because Aristotelian logic is a strange theory, so of course you cannot criticize Aristotle because he was the first one who invented logic. So maybe it was not possible to do it otherwise, but still he invented the first theory of logic. But because this logic was a theory of arithmetical structure, so without ontological reduction, in order to make logic suitable for mathematical purposes, like Frege wanted, he had to introduce ontological reduction. So he had to change the idealizations. He had to change the whole framework, how the language works. So he introduced these two reductions and three syntheses, and that is how logic works. Thank you very much.